Okay, we're going to start chapter 9 here in this video, where we're going to be moving away from confidence intervals and looking at the second type of statistical inference, which has to do with significance tests. There are two main statistical inference methods that we study in AP Stats, and we're just coming off the heels in Chapter 8 of having spent a lot of time looking at confidence intervals. The purpose of a confidence interval is when we're trying to estimate the location of a population parameter, often a population proportion or a population mean. And we learned that when we do that, we're essentially creating a range of possible values where we think that population parameter is located. When we shift to a significance test, what we're doing in a significance test is we're not trying to estimate what a population parameter is, but instead we're given some type of a claim that is made about a population, and then we're trying to assess the evidence that would be provided by our data to try to figure out whether we should either reject that claim that was initially made or whether we would fail to reject that claim. Okay, please take note that I didn't say reject or accept the claim. We never accept a claim. We either reject it based on the evidence that we collect from our sample, or we simply say the evidence is not strong enough, therefore we are failing to reject, meaning we're not going to reject the claim, but we never accept the claim, okay? So if we're wanting to assess the truth of a claimed population parameter, what we do is we always begin these significance tests under the notion that the claim that we're given is true. Okay? It's kind of like the court system. When someone goes on trial, they are always assumed that they are innocent until they are proven guilty. And so we always start with the assumption that the claim that is made is true. And then the process is we then gather a sample, and if the sample that we gather feels like it's different from the claim that's being made, there is essentially one of two explanations for that difference. Option number one is, no, the claim that was made is actually true. The reason that our sample is appearing different than what was claimed is just merely due to sampling variability. We know that when we draw out samples, they can vary from one sample to another, and it was just by sheer happenstance the sample that we happened to draw out was different from the claim just because of sampling variability. The other option, if our sample is different than the claim, is that the claim was actually false. And so the reason that our sample is different is because the claimed population parameter is in fact false. Okay? So we tend to use probability to determine which of those two statements above that I highlighted there is more likely to be true. All right? Now, if the probability of getting a sample like the one we got, assuming again that the claim is true, if the probability of getting that sample is small enough, and by small enough we mean less than 5%, then we're going to conclude that the assumed claim is actually false. But if the probability of getting a sample, like the one we got, under the assumed claim is not small enough, meaning greater than 5%, then that means we do not have enough evidence against the claim to refute it. Now, it's still possible that that claim could be false, but the evidence provided in our sample is not strong enough for us to say that we're going to reject that claim. Okay, and so in statistics, this process that I'm kind of just laying out the groundwork here right now that I'm describing is called a significance test or a hypothesis test. Okay, and there are certain steps to a significance test. It always begins by us defining the parameter from which the claim is being made about. So there's usually a claim made about either a population mean or a claim that's made about a population parameter. Okay? So this is exactly how we started all confidence intervals, by the way. We always started by defining the parameter that we were trying to estimate. Okay. The next thing that we would do in a significance test is we would want to define what the claim is, and this is called the null hypothesis. Incidentally, the null hypothesis always contains an equal sign. Okay, we designate a null hypothesis by using the symbol capital H with a sub-zero. It is also worth noting that your hypotheses, both the null and the alternative, are always statements that are made about a parameter, never about a statistic. So this should always be either mu or p, never an x bar or a p hat. Okay? All right, and so then the next step would be to define the alternative hypothesis. This is what you're actually trying to prove instead of the claim, which is the null hypothesis, okay? You want to have evidence in support of your alternative hypothesis, and that evidence is provided from the sample that you would gather. Now, the alternative hypothesis always has an inequality symbol or a does not equal to symbol, and the symbol that we use to designate an alternative hypothesis is always H sub A. And so, once again, these alternative hypotheses are always about a parameter, okay, never a statistic, so mu or p, okay, or your alternative hypothesis, could be a statement where you're saying it does not equal a certain number. Okay. And then at the end, you would draw a conclusion. Again, please note that your conclusion is either to reject the null hypothesis, that's the claim, or to fail to reject the null hypothesis. We never ever accept the null hypothesis. Okay, that is never an option for our conclusion here. Okay, so in terms of our null hypothesis, that is always some type of a statement of no difference. And by no difference, I mean that is where we put the equal sign. Always, the null hypothesis is always the equal sign. The alternative hypothesis is one of these three options. It is either a less than, a greater than, or a does not equal to. Okay? If the alternative hypothesis is a less than or a greater than, like these two right here, we call that a one-sided alternative hypothesis when we use those symbols. If the alternative hypothesis is a does not equal to, then we call that a two-sided hypothesis, okay? Now, we always want to determine and draft our hypotheses, both the null and the alternative, prior to collecting our data from our sample. You never want to look at what your sample is, and then after you've looked at it, then determine what your alternative hypothesis is. That would not be good statistics here. So let's practice just looking at a problem and seeing if we can draft what we think the null hypothesis would be and the alternative hypothesis. And actually, just flipping back to the previous page here, prior to identifying the null and alternative hypotheses, we always want to start by defining the parameter from which the claim is about. And so here, this is talking about a high school junior running for student body president. Her name's Sally. She claims that 77% of the student body favors her in the school election. Her opponent believes that this percentage to be lower. Very important word there. Her opponent believes it's lower. State the parameter and then write the appropriate null and alternative hypotheses. Well, the parameter that's in question, this doesn't feel like it's a mean. It feels like it's a proportion. Okay, so we're going to use a P and we're going to define that. Make sure that we're using, this is the true population proportion, okay, of students favoring Sally. Okay, that is the population parameter. Now remember, our null hypothesis is always a statement of equality, and it's always a statement made about your population parameter, which would be the true population proportion. Okay, she's claiming that 77% of the student body is in favor of her. The alternative hypothesis is what her opponent is believing, which he thinks that it is lower than that. And so he thinks that the true population proportion in favor of Sally is actually less than 0.77. So that would be the null and alternative hypotheses here. Okay, let's look at another example. We're going to take this a little bit further here so that we can dive a little bit deeper into these significance tests. Here, this next example has to do with Ricky Bobby. It says he's a hotshot basketball player here, and he claims that he can make 80% of his free throws. Now, you think that he is actually a liar and that he doesn't make shots as frequently as he claims. Now, we're wanting to conduct a significance test in an attempt to disprove Ricky Bobby's claim. First, though, we want to define the parameter and set up the null and alternative hypotheses. So we're going to let P be the true population proportion of made free throws by Ricky Bobby. Okay, so that's his actual proportion of made free throws here. Okay, now let's draft our null hypothesis. Again, always a statement of equality. Our parameter is a P. His claim is that he's an 80% free throw shooter, and we think he's a liar, and he doesn't make these shots as frequently as he's claiming. So that means we would be suggesting that the alternative is actually a less than 0.80. Okay, so let's say that we were to collect data to look for some evidence that maybe would be going against his claim that he's an 80% free throw shooter. And let's look at just 3 possible samples to kind of judge what we think the strength is from each of these 3 samples, how that is either evidence against Ricky Bobby's claim. So let's say in sample 1, we have Ricky Bobby shoot 100 free throws, and of those 100, he makes 82% of them. Okay, kind of feels like maybe we wouldn't reject his claim. Feels like, okay, maybe Ricky Bobby actually is an 80% free throw shooter. In that sample, you know, the evidence there was showing that he was shooting at 82% of the time. But look at sample 2. Okay, if that was the sample that we collected, he's only making 14% of his shots. That feels like that's really strong evidence to say that we might want to reject his claim. Okay, but what about the situation in sample 3, where he shoots 100 shots? Yeah, he doesn't make 80% of them, but wow, 78% really feels like it's close to 80%. Like when you're an 80% free throw shooter, you know, maybe sometimes you make a little bit less than 80%, sometimes you make a little bit more. So it becomes a little bit more challenging when the data that we collect is maybe really close to the claim and just a little bit under in this case. It makes it difficult for us to kind of judge, you know, should we actually be rejecting his claim or should we not? So we need to come up with some type of a way to kind of quantify the strength of the evidence that we're seeing in our sample, and how strong is that evidence really against the null hypothesis, and then we can use that to kind of draw our conclusion. Okay, so let's say that we were going to have Ricky Bobby shoot 50 shots, okay, 50 shots. And let's just say that of those 50, he made 32 of them, okay? Now this is our sample, so I would be labeling this as a P hat. 32 out of 50 would give us a 64% rate that he's making these shots, okay? And so the question is 64% strong enough evidence to call Ricky Bobby a liar? Like, at what point are we feeling safe enough to say, I'm going to reject your claim? Okay, so here's what we're going to do. We're going to run a simulation. Okay, and we're going to run it under the assumption that what Ricky Bobby is telling us is true. Okay, so when we do this simulation here, and I'll lay out how this would be done, and we have a dot plot already on the next page here that we can look at. But that's what we're going to be kind of taking a look at. So let's flip here to the next page here and take a look at this notion here that when you do a significance test, it is always run under the assumption that the null hypothesis is true. Okay, so you design the simulation under the conditions that the null hypothesis is true. So in this case, the simulation would be ran assuming that he really is an 80% free throw shooter. And then we would want to see in how many of those samples from our simulation is he actually shooting only 64% or something worse than 64%. Okay, so here's what we would want to say. We would want to say, based on the evidence, we could conclude that Ricky Bobby's claim is incorrect. But in reality, there are really only two possible explanations for why in the sample he only shot 64% of his free throws, or he only made, I should say, 64% of his free throws. So here's one explanation. One explanation could be that Ricky Bobby's claim of being an 80% free throw shooter is actually correct. He is legitimately an 80% free throw shooter. The reason that he only shot or made 64% of his shots in the sample was just by some horrible luck, where this would only have happened under the rarest of circumstances, like less than 5% of the time. It's so unlikely to have occurred, but truly he is an 80% free throw shooter. Or the other explanation for why he only made 64% of his shots is because the population proportion of him shooting and making these shots is actually less than 80%, meaning he's not an 80% free throw shooter. So, more often than not, he would actually be shooting well under 80%. Okay, so here's the basic idea with these significance tests. An outcome that would rarely happen if a claim were true is very good evidence that the claim is not true. Okay? So let's go back to looking at this simulation here. Okay, you see all of these dots here in this dot plot, and I'm just going to set up what would have taken place to create these dots. Okay, remember, he shot 50 shots, and so maybe on our calculator we would assign the numbers 1 through 40 to maybe equal a made shot, and we would let 41 through 50 represent a missed shot. And then we would take our calculator and we would randomly generate 50 numbers between 1 and 50. Okay, and we would tally up how many of those numbers were 1 through 40. And we actually would want to allow repeats in this instance because all the numbers 1 through 40 just represent whether he made the shot, and 41 through 50 just counts as a miss. And so we've got it set up where we are assuming that his claim is true. 40 out of 50 is 80%. So we're setting it up where 80% of the numbers count as a made shot, and only 20% of the numbers here count as a missed shot. Okay. So what we would do is we would generate 50 numbers between 1 and 50, count up how many of the numbers were 1 through 40s, and out of 50, we would put a dot on the dot plot here for the proportion of made shots. And so it says here that they did this 400 times, creating 50 shots, 50 shots, 50 shots. And we're setting up, these are the proportion, the sample proportions of made free throws. And so what we're looking for here is we're trying to figure out in all of these 400 simulations, how many times did we get a sample proportion of being either 64% or something less than 64%. Okay, what's the likelihood of that happening? So we want to find what is the probability that a sample proportion would either be 64% or less. And in these 400 simulations, only 3 times did Ricky Bobby in these simulations shoot 64% or less. That is a very small likelihood of happening. In fact, it is not even 1%, it's like 3/4%. And so what we're saying with this is that these 3 dots right here, that this isn't likely to happen. Okay. Now, if it wasn't very likely that he's actually an 80% free throw shooter, and yet he would shoot and make only 64% of those, then this means that we should reject the claim, because it's not very likely that he should have made 64% of his shots if he's actually an 80% free throw shooter. That's only a 0.75% chance of happening, okay? Very, very unlikely that would have occurred if he's truly an 80% free throw shooter. And so what we call that 0.75%, that is called in stats a p-value. And what the p-value is, it's the probability of computing, assuming that your null hypothesis is true. It is a probability that your statistic, and in this case, the statistic was a p-hat, would take on the value that you got, in our case 64%, or something even more extreme, that's why we said less than 64%, okay? So let's interpret our p-value of 0.75%. I'm just going to write that here. P-value equals 0.75%. Okay, we need to get comfortable with interpreting these p-values. We're going to get lots of practice with this. This is just the first introduction to this, but you always start by saying that we had assumed that the null hypothesis was true, but we want to say it in the context of the problem. So we're going to say, assuming Ricky Bobby is an 80% free throw shooter, or an 80% shooter, okay, there is a 0.75% chance of getting a sample proportion of 0.64 or less, okay, or more extreme. And in that case, we're talking about or less than that. Okay, very, very unlikely that he would have made only 64% of his shots there. Okay, so we're going to look at this last page to wrap up this video here. The final step in a significance test is for you to draw your conclusion, and you're drawing your conclusion based on the p-value that you're getting from your sample. Okay, and we have that set up there. Our p-value from our simulation was 0.75%. Now here are your two possible conclusions. You could either reject the null hypothesis, which means you're actually accepting the alternative, or your other conclusion is that you fail to reject the null hypothesis. Please note that under no circumstances do we ever accept the null hypothesis. Okay, so if your p-value is very small, okay, usually less than 5%, that is when you reject the null hypothesis. You say, look, this is convincing evidence against the null hypothesis because there was such a small chance that what happened in our actual sample could have happened if your null hypothesis were actually true. The other option is if the p-value is large, like greater than 5%. Well, then we would not reject the claim because we're saying we don't have convincing evidence to reject it. There was a larger chance that that actually could have occurred, assuming the null hypothesis is true. Okay? Now, there are significance levels to these significance tests. It is often 5%. The significance level is denoted by the Greek letter of the alphabet, alpha. It is often 5%, but sometimes in problems they will name it as being 1% or 10%. Okay, so whatever percent is defined as your significance test, you're going to compare your p-value you got to your significance level. And if your p-value is less than your significance level, you will reject the null hypothesis. If it is greater than your significance level, you will fail to reject the null hypothesis. Okay? So, your results are considered statistically significant if you reject the null hypothesis. Okay, when you reject a null hypothesis, that is when we say the results are statistically significant. So in this example, we had a p-value of 0.0075. Obviously, that would fall less than our alpha level of 0.05, so we would conclude that we are rejecting the null hypothesis. Here is the proper way to draft a conclusion to a significance test. you should state since P, which is 0.0075, is less than the alpha level of 0.05, we reject the null hypothesis. Okay, that's your first statement. And then you go on and say, we have convincing evidence that, okay, now if we're rejecting the null hypothesis, that means the evidence is now in favor of the alternative hypothesis. If you think back a few pages earlier, what we drafted for the alternative hypothesis, we said Ricky Bobby's true population proportion of made free throws is lower than 80%. Okay, we had a less than there. Okay, we will definitely be getting more practice with drafting these conclusions, and we're going to learn how to get the p-value from actually not just doing simulations, but that is the idea with just this opening example here. Okay, there's a few problems for you to go ahead